intervals for which we are increasing, decreasing, or staying constant. So I'm going to talk about each one of these particular intervals one at a time. I'm going to start with the idea of what it means for a function to have an interval on which it is increasing. Okay, so the setup is going to be the same for all of these. So we're going to start by talking about what it means for a function to have an interval where it's increasing. So for sake of looking at pictures here, right, give yourself a coordinate plane, something like this. We got x and y. And we're going to give ourselves any old generic x, so I'll call it x sub 1, and any old generic second x, I'll call it x sub 2. All right? The only thing that I know about them is that x sub 1 is less than x sub 2 because it's closer to 0 on the number line. This is going to be my defined interval. All right? And I'm going to define it as with a big capital I, interval I. So let's give you a function, and let's give you a function that looks kind of like this. All right? Here's my function f of x. And within that function f of x, right, if this is x1, then this is f of x1. And if this is x2, then this is f of x2. And that's pretty much all the general information I could put onto a graph. Now, in layman's terms, instead of just looking at this graph, right, from left to right, as we read books and as we look at graphs and as we look at information on number lines, from left to right, yeah, it looks like the graph is getting bigger when I move from left to right. But how do we use mathematics to actually convey that, and the notation that we use, how do we write it down? So what I'm going to do is I'm going to give you a setup that's going to be if, when, and then. It's going to be the setup for all three. So if, when, and then. Here's the setup.
What is the thing next to the...
This one?
Yeah, what is that?
F of x1? F of x, just the output, inputs and outputs. So here's the deal, all right? If f of x1 is less than f of x2. So let's go look at the graph, and let's make sure f of x1, here's f of x1, here's f of x2. Do you agree that f of x1 is less than f of x2? Yeah, because it's on the y-axis, the f of x1 is definitely lower. So if this is true, when x1 is less than x2, so take a look at the x-axis. Is that true? Is x1 definitely less than x2? Yeah, it sure is, right? So if the output for f of x1 and f of x2 obeys this little inequality, when x1 is less than x2, then we can say a function is increasing, I'll just use inc, on interval I. All right? So this is the rule, the if, when, and then. So if your outputs, f of x1, is less than f of x2 whenever x1 is less than x2, then you're guaranteed that on that particular interval, your function is defined to be increasing. So the goal here is for you to be able to look at the stuff on the right-hand side and relate it back to the graph on the left-hand side. So do all of these notations and inequalities make sense to you? That's the question you should ask yourself. Do you know what f of x1 is? Do you know what f of x2 is? Can you read that inequality, and does it make sense? And we're going to give ourselves two generic x's for decreasing. So here's x1 and here's x2. And we're going to define our interval between x1 and x2. And the interval is going to be defined as I. And I'm going to give you a function. And your function will look something like this. Okay? There's my function f of x. So I have inputs of x1, I have outputs f of x1, and I have an output f of x2. Right there. Oh, sorry, right there and right there. All right, so same setup. If, when, and then. So, if, what do you think this is going to be? Take a look at the graph and relate to what we just did in the first one. How is f of x1 and f of x2 related to each other? There you go. So if f of x1 is greater than f of x2, so if my outputs, right, greater than, when what? What's still going on the x-axis between the x's? How are they related? x1 and x2, how are they related? x1 is less than x2, then we can say a function is decreasing on interval I. So that's what it means to be decreasing, right? In other words, function is going down on your interval. So our whole idea here is defining these intervals. Right? What do you think then? Okay, so for a constant function, right, it looks like it should, right? So going from left to right, the function is neither increasing nor decreasing, it's staying constant. So the way that we describe this is we're going to say if the outputs are the same, so in other words, if f of x1 is actually equal to f of x2, when x is in the interval, okay, the reason we say when x is in the interval here is because the output is the same no matter which x's you pick. So it doesn't necessarily have to be that x1 is less than x2. Any of those two, if the outputs are the same for x1 and x2, then we can say f is constant on interval. Nice and big for you. Okay, so, oops, I want red. So check this out. This is my function f of x, right? There it is right there. So, looking at this function, would you agree that it passes the vertical line test? Yeah. Yes. Okay, good. And this particular function has 3 intervals on there, okay? It has 3 intervals, and some of these intervals are decreasing intervals, and some of them are increasing intervals, okay? So I'd like us to sort of discuss, do you see an interval for which this function is decreasing, and how would you describe it? Now remember, we're talking about intervals of x values. So we're only talking about x values. Anybody see one? Seth, what do you got, dude? From negative infinity all the way up to 0, all the way up to there, what would be, it would be decreasing. So one of the intervals that we've just talked about is from negative infinity up to 0, and we have a parenthesis. So that's one of them. Did everybody see that? Mm-hmm. Okay. There's another one, too. Yeah, what do you think, Bailey?
0 to 3?
Nope. Well, I mean, sorry. For decreasing. Anybody see another decreasing?
0 to 2.
No, not that one either. Cindy, what do you think? 2 to infinity. From 2 to infinity. Very good. So from point 2 all the way to infinity is another spot, another interval where my function is decreasing. And the reason is because from 2 to infinity, it defines for every output, right, in my interval, f of x1 is smaller than f of x2. Does that make sense? Okay. Where is the increasing interval? Yeah, what do you think, Maddie?
0 to 2.
Yeah, in between, right? So in between from 0 to 2, we have our interval is increasing. So we would say increasing on 0 to 2. Now, question for everybody. Why do we have parentheses all over the place, and why are there no brackets used on any of these intervals?
Infinity doesn't end, so you can't.
Yeah, infinity, we got that one covered. There's no end to it, so we never use a bracket around that. But how about the 2 and the 0? How come we don't use it there? What's that? Yeah, it's not. It's so right at these points, right? When x is 2, the output, there's f of 2 right there, the output here, the graph is neither increasing nor decreasing, nor is it constant for any interval. That's actually called a point of inflection. We don't need to know that yet, but at those points, it's neither increasing nor decreasing, nor is it constant, so we don't include them in the intervals for decreasing and increasing. Does that make sense so far? You guys cool with that? All right. Take a look at this. So, first of all, is this thing even a function? Yeah, okay, hands up for yes. 2 people say yes, 3 people say yes. Hands up for no, this is not a function. I got 4, 5. Hands up for you're not sure if this is a function or not. Good. 1, 2, 3, 4. Okay, 5. This is a function. Who can defend why? Yes, Bailey.
Because the dots are open, meaning that it's not including that point.
Yes, very good. Does this graph pass the vertical line test? It sure does, right? Even though there's this gap in between there, right? If you have a vertical line, there is only one output for when x is 0. So when x is 0, what's the output, everybody? 3. Very good. All right? So this does pass the vertical line test, though this is a function, even though it looks funky, because there's a gap there, it is still a function that does pass the vertical line test. Okay, so now, let me ask you a question. When, on what interval is this graph decreasing? Yeah, Matt. It doesn't. Very good. None of those exist. Okay. On what interval is this graph increasing? Yeah, you can just shout it out. What do you got? 0 to infinity? Well, funky. Now, do I include the 0 in this particular case? No, why not? Because not good. Where is this interval? Constant. Good. So negative infinity, comma 0, bracket, because 0 is included on that one, right? Up to 0. You guys feeling good about that? This is constant. This interval, the function is staying constant. You feeling good about that? Okay. This interval from here over, the graph is increasing. The graph is never decreasing. Yes. Yeah. Sorry, that should be as negative infinity. Sorry. Good call. All right. So even and odd functions are defined as the following. So if you have f of negative x, and it's the exact same thing as f of x, then you have what's known as an even function. So f is even. All right? We'll talk more about that. And if your function is even, it implies that it is symmetric with the y-axis. Now, have we talked about symmetry before? Or have you heard symmetry before? Yeah, okay, so what is symmetric with the y-axis? What does that mean? What does it mean? Okay. So same on either side of the y-axis. It's like someone put a mirror on the y-axis, and when you looked into that mirror, you'd see exactly the same thing on either side of the y-axis. So it has symmetry. Some functions are even. If that's the case, then f of negative x will be the same as f of x, okay? Now, some functions are odd, and that is the case is if f of negative x is equal to the negative of f of x, then we say f is what's known as an odd function. If your function is odd, then we're guaranteed to have symmetry with the origin. Now, what does that mean? What's symmetry with the origin mean? Anybody have any ideas? Thoughts? So symmetry with the origin, yeah, Seth, what do you think, dude? Not necessarily all four, but if it's the same distance away from the origin on one side, then it's the same distance away on the opposite side from the origin in the other direction. And we're going to explore these if I had more than 7 minutes. So we're going to definitely come back to this on Monday. Okay, so let me give you some examples here and talk about how you can determine if a function is even, odd, or neither, and this is the last idea for the day. So I'm going to give you a function. I'm going to give you f of x is equal to, how about x squared plus x? And the goal here is to determine whether or not this function is even, odd, or neither. All right? So what we're going to do is we're going to check, okay, let's take f of negative x. How do I evaluate f of negative x? I just simply plug in a negative x wherever I see an x. So that's going to give me negative x squared plus negative x. So what is negative x squared? What does that simplify to, or how do we take care of that situation? What does that become? Positive x squared. Very good. Plus a minus x gives me a minus x, right? So here is f of x. It's just x squared plus x. Here is f of negative x. It is x squared minus x. So what I want to do is we're going to compare these two. Are they the same? No, they are definitely not the same. Therefore, according to this, there's no way this function can be even, because f of negative x is not the same thing as f of x. You with me on that page? Yeah? Okay, now, let's try this. Let's compare the negative of f of x. Well, that literally means put a minus sign in front of everything that f of x is, x squared plus x. And then we're going to distribute. That gives me negative x squared minus x. So here is negative f of x, and I'm going to compare that to f of negative x. Are those the same? Yes or no? No, those are definitely not the same either. So it can't be the case that f of negative x is equal to negative f of x. Therefore, this particular function right here is neither odd nor even. None. It's none. So therefore, this implies there is no symmetry. Okay? Okay, I have 5 minutes. Can you, Tess, will you close that door? Because I want to give you another example here. Okay? Let's do B. All right. Let's talk about this one. Let's do f of x is equal to x squared minus x to the 4th plus 1. All right? Good. There's the original function right there. All good to go. Let's take out f of negative x. So I'm going to do negative x quantity squared minus negative x to the 4th plus 1. You guys with me so far? I'm just replacing x with a negative x. You good there? Okay, negative x squared becomes a positive x squared. Okay? Negative x to the 4th becomes a positive x to the 4th, then minus. So positive x to the 4th, and then I have a plus 1. So here's f of negative x. It is x squared minus x to the 4th plus 1. Okay, now let's compare these two. Are those the same? Yes. Those are the same. Yes, they are. So what does that imply? It implies that we have an even function, and that implies that we're going to have symmetry where? Over the y-axis. Very good. Okay? Now, I actually have that one somewhere. Where is it? That's not it. Is that it? No. Which one was it? There it is right there. There we go. X squared minus x to the 4th plus 1. So take a look. There's the graph. This is what's known as an even function, and we can tell from the graph that it is symmetric over the y-axis, right? It looks the same on both sides of that y-axis. Does that make sense to you? Feeling good? Okay. I do. Yeah. Some functions like this, like that very first one that we did, is neither even nor odd, and it has no symmetry. Okay? That's how some functions are. Okay, the last one is going to be an odd function, and I'll leave it to you to try and run. So 2x to the 3rd minus 6x to the 5th. All right? I'm going to stop it here, and I'm going to let you solve this one, and I want you to take a look at negative f of x and see what you get. Okay? And then also look at f of negative x and see what